Okay, so first of all, thank you very much for just providing a detail related to my profile. And I'm really honored here to be invited from your side to take these sessions in your scheduled FDP. It's really a pleasure moment for me also to again go for taking a session for the faculty members. So being a practitioner and a researcher of a quantum computing, my responsibility is now a very different one, because the people have been learning throughout. That is since the last 4 days through that is the concept related to quantum computing algorithms. Okay, now the context may be changed. Now the people are moving from the algorithmic part to the machine learning domain. Okay, so I'll try to just make all the faculty members. As I can see, there would be 243 people online available. Okay, so how many are the registered participants, sir? Can I be known? Hello?
Around 445, sir. Regularly, I am getting 320, sir.
Okay, great, sir. It's
so
really
due to break, I have given a break.
Okay.
Most probably, people are again joining, but we will definitely reach 320, sir.
Okay. So we should start our session, or should
Yes,
wait
sir.
for 2 to 4 minutes?
We could start, sir. We should start. No issues.
Okay. Thank you very much. So again, once again, thank you, Murthy sir, for giving me the opportunity and to take this session. We will be again connecting day after tomorrow with another that is machine learning session again. Okay. So first of all, let me share you with my screen. You just please signal any participants, if you may just let me know your status, whether it is visible or not. Just please.
Yes, you are presenting it short.
Now, is it visible?
ATAL online, it's visible.
Thank you very much, sir. So let's begin here with the talks related to the quantum machine learning aspects. Okay. So here again, we are going to take day 4, session number 8. That is based on a quantum machine learning foundations. Okay. So I'll try my best to all of you connected in the field of quantum machine learning. Okay. So these are some outlines of the session. So initially we will start with some quantum machine learning significances. Followed to that one, we will check over the state preparation and the data encoding methods, because I'll let you know first that why is the need or why it is required to have the data encoding initially when we usually work for any of the machine learning related domain. Okay. Followed to that one, we will have a talk related to the feature mapping and using kernels and the quantum machine learning other essential parts or tools that we will also be discussing here. Followed to that one, some design methods and some current challenges, some basic challenges what are still a kind of open problem that is remaining with the quantum machine learning domain, that I will let you know. Followed by few of the applications I will discuss, and a concluding remarks with some list of references. Okay. So here start with the context that we are here going to learn a quantum machine learning. Okay. So now we people are known, that is the context of the two things are basically integrated together. Okay, like a machine learning aspects and the quantum computing aspects, both techniques are basically integrated here to form this QML concept. Okay, so if you see this Venn diagram first, okay, this is the machine learning part, this is our quantum computing part. Okay, and we have just integrated both of them, means we have taken the intersection of both of them in order to explore the domain of quantum machine learning. Okay, so before proceeding to our session, we should be, because you people have been learning out this quantum computing algorithms and the basics, fundamentals, or all things along with the quantum programming. Okay, so now I am assuming that you people are enough ready to just directly understand with the concepts or the things we people are just going to discuss in the today's session. Okay, so now the context is again coming to our mind, that why we people are actually looking for a quantum computational aspects. Yes, so in a very simple word, I may let you know, that is the concept of quantum computing that is to realize basically an exponential number of operations in just a single step of execution. That is a privilege that can be given by the quantum computing phenomenon. Okay, so we have some computational model. That computational model is giving us a flexibility to realize exponential number of operations in just a single step of execution. Yes or no? If any one of you may respond through your voice, so it would be good to connect in throughout the session. Okay.
Right, sir. So
Okay.
whatever problems classical computing cannot solve, quantum has a promise of solving it quickly.
Yes. So basically, we always look for the two context. Okay, that is the first thing. That is, as per the definition of the quantum computing, we are looking for the exponential realization of the operations in a single step of execution. Okay, this is as per the basic context. Second thing, and the two main things for which we people are actually applying the quantum computing. That is the first context, when for a certain problems, if our classical machines remains inefficient to solve, so for such a problems we usually apply the quantum based solutions. Okay, so that some speed up results we may achieve. Now another fact is that sometimes it happens that the problem is solvable in a polynomial time, means we have the efficient solution, but the data which is involved to process that particular problem, okay, that data is not very small. Rather, we used to call it as at least an exponentially large data. Okay, so if we usually deal with exponentially large amount of a data, volume of a data, or the data is having very exponentially high dimensions, okay, so for that problem again our classical inefficiencies remains. So for those aspects we are actually applying the quantum computing factors. Okay, and we know that the machine learning as one of the basic subset of the AI field, okay, that is allowing us to just learn the patterns from the data itself and without being explicitly programmed. So that is the key context. We people are here to understand with some patterns from the data itself. Okay, but to understand the patterns from the data, sometimes it happens that the classical machines may not remain efficient. So only for those purpose, we will be applying some quantum based solutions. Okay, so I think this concept must have been discussed to you in the earlier sessions also, but I am just again clarifying. Just do not assume at all that a quantum machine would be a replacement to a classical machine. This would not be like any factor. Okay, you have to assume, like earlier we people were used to understand the superscalar architecture. Yes or no? Just like a superscalar architecture, initially the tasks comes to what? The scalar processor in a classical computational aspect. Okay, so when there exists some classical inefficiencies to process the data in a scalar way, then we have to hand over the same task to the vector processors. Yes or no? Yes, like this is one form of the that is computing architecture. Yes or no? That is, the scalar processing is first, followed by a vector processing. Okay, once the vector processing gets done, the outputs comes back to a scalar processor, and from a scalar processor again the end user may retrieve the output. So similarly the things would happen here. Initially the task should come to the classical machine, when the classical machine will realize some inefficiencies, okay, in order to solve a problem, whether it belongs to the hardness of the problem or it belongs to a challenge of processing the data associated to the problem. Based on either of these factors, the classical machine realize, okay, there exists some inefficiencies, so for that purpose only the same task would be handed over to the quantum machine. And we know once the quantum machine executes the task, the quantum would have the different representation of a data. Do you agree or not?
Yes, sir.
That is the first thing we should be agreed. Okay, like what we talk about, if we talk about a classical processing, we have a bit, and bit must be having what? At the lowest level of processing we have the bit instances either as 0 or 1. Yes, but instead of a bit, what is available here in quantum?
Few bits, sir.
That is a quantum bit. And what does the mean of quantum bit?
It can have simultaneous state of 0 and 1 at
Linear,
same time.
linear combination of zeros and ones.
No, still somehow that linear
Superproportion of
combination,
the particles.
Simultaneously 0 and 1. So it will maybe be having any state of 0 and 1 until it is measured.
it's okay. Linear combination, superposition, both things are acceptable. But the thing is, it is not like a 0, 1. You just try to understand the set. It's a set of what? Cat 0 and cat 1, if you remember. Yes? It's not like 0, 1. The superposition will be realized. The linear combination would be realized by the machine. But it is not for what? The zeros and ones. Rather, it is for what? Cat zeros, cat ones. I think you people may be able to recall. Okay? Is it fine?
Yes, sir.
Yes, yes.
Okay. So you please try to just recollect your whatever the things you have been learning out throughout, that is the since your start of this FDP. So the thing is that instead of having a bit, we have the different form of the information. So means the information processing system here in quantum is completely different from what? The classical processing system. Like in a classical, we can take these as a scalar values like zeros, ones. These are the simple representation of the values. But here in a quantum, these information are somehow different. These are not scalar, rather these are vectors. Yes or no? How do we write the 0? The 0 is what? It's a two-dimensional vector. Are you agree? Do you agree for this one? This
Yes.
cat 0 is 1, 0. That's
Yes,
a 2 cross 1 vector. Similarly, this 1 is actually a 0, 1. It's again a 2 cross 1 vector. So if you are talking about a single qubit, so that single qubit may be there in either of these states like cat 0 and cat 1, as well as it will have a privilege to realize the linear combination of cat zeros and cat 1s. Okay, means the linear combination of a vector would always be there. Okay, that we usually understand with the phenomena of superposition. Okay, so this only the property that is realized by a quantum mechanics. Okay, and that has been incorporated in a computational power. So we emerged with a quantum machine. That is the basic or the fundamental thing actually got developed. Okay, by the industries also, because industry is really playing a very great role for the realization of the quantum machine development. Okay, so now based on the same fact, I am letting you know that why we are only emphasizing on the quantum computing, because this is the first thing. Instead of having a bit, what we are having here, that is a quantum bit. And now you know what is the quantum bit. It's a vector of information. It is not like a scalar values. Understood? Yes.
Yes, sir. Yes, sir.
Okay, so it would be what? That is a cat 0, cat 1. Now follow to that one, that this qubit must be realizing a property of superposition. Superposition means a linear combination of the quantum states. So these quantum states, like if you remember your earlier days of your studies, there is a representation of every qubit. Okay, and that representation we used to call it as what? Block sphere. Yes. Yes. That spherical model is there, that we used to call it as like this. That is called as what? Block sphere. And if you see that block sphere, so at that north pole we will have what? Cat 0. And at south pole what we have? That is cat 1. That is just a simulation of electron spinning states. The electron may be there in a ground state, like electron may be there in an excited state or in a superposition of both. Similarly, the electron spins may also be assumed like either available in an up spin or in a down spin or in a superposition of both. Yes or no? So the thing is that like a representation of a qubit, that information is always let us know that qubit, like a quantum state 0 is available at a north pole and a quantum state 1 is available at the south pole. It is just like a earth sphere. Okay, So at a meridian, like at a zero meridian line, we people are having these two of the basis states. And once you explore the superposition, it means simply that these quantum states like cat 0, cat 1, both are simultaneously appearing. Okay. So the thing is that the first motivation, what we people are going for, why we people are going for a machine learning aspects, that is the first thing that we need to understand, that is a qubit which are realizing superposition. What about the second thing? The quantum entanglement, because we do not deal with a single bit or single qubit of information. Yes or no? We usually deal with what? The information which is kept in a register. Yes or no? That is at the architecture itself. We usually keep our information in the form of register. So the thing is that if you are going to process your register, somehow your information must be entangled. Okay. Entanglement means what? What does the basic meaning of an entanglement? That we usually consider it to be a strong connection among the qubits, or you may call them as a correlation among the qubits. Yes or no?
Yes, sir.
Okay, that what we used to call it as, you must have learned the concept of, suppose that we usually call it as Bell state realization. Yes, like for the form of the entanglement. Okay, where we usually use the two qubits. So at the first qubit we apply what? Hadamard gate. And by taking the same qubit as a control, we apply the control NOT gate, that is the NOT operation on the target qubit. So once you have a circuitry like Hadamard followed by a C0, it would realize a maximally entangled state. And that maximally entangled state would be called as what? The superposition of the two states. That is the entanglement of the two states, what we used to call it as. Okay. So the thing is that entanglement must remain present in your system, and the parallelism, it's all about the parallelism only, because we people belong to a computer science. We always look for parallelization of the tasks. Okay, so this is our inherent nature. Like if we talk about the humans also, the same things we people are actually mimicking in what? The computational models. So like we people used to process, okay, the similar things we want to process is through the computing machine. Okay, now you people have analyzed this fact or not. Whenever we people being a human, we are going to take any decision based on a condition. Any condition suppose arises. Okay, so based on that condition, we usually take some decisions. Yes. So once we start thinking to take a decision, do we remain in a simultaneous superpositions or not? Can you be able to that is visualize by your own?
Yes, sir.
Whenever
Until decision is done, it's a probabilistic outcome. So we are always keep thinking of multiple outcomes.
yes. So but we always consider these decisions, okay, in a superposition of things or not. Like suppose, okay, let me give you one basic example here. Okay, you just try to understand that what is actually a decision I am talking about, because this is relating to a machine learning model here. Okay, suppose I have given you one of the image, okay, like an image. I am going to just show you that image belongs to a cat, suppose. So if that image belongs to a cat and I am asking that is this a cat or not? Okay, so a very tiny part of the time we usually take for processing, we usually check for that what? We usually check for what? That image, process through our neurons, we check it. Yes, is it a cat? Then we immediately declare, okay, it's cat. Okay, but before declaring whether it is cat or not, we were there in a superposition of the two things. Okay, either I should declare it as cat or I should not declare it as cat. Yes or no?
Yes, sir.
Okay, we always remain in a superposition of things. If suppose the picture what I am showing, that is not belonging to a cat, and I am asking, means I am taking a picture of an apple and asking whether it is cat or not. So you will think first, Okay, whether it is cat or not. No, it's not a cat. Yes. So the thing is that, but before declaring the thing or before giving our decision, we must be there in a simultaneous superposition of yes, no, yes, no, yes, no. Yes. So what does it mean? Whenever being a human, we usually take a decision. Okay. So before that decision also, we always realize superposition in our mind. Okay. So if we always remain in a superposition of our mind, okay, so the same aspects are here to be mimicked in a quantum machine intelligence format. Okay, so now the age is come. Okay, not only the artificial intelligence things we people are looking for, we'll be dealing with what? The quantum based artificial intelligence, like you may call it as quantum machine intelligence. Okay, so now the thing is all about parallelism. Okay, so the parallel things must be taken care. Okay, we want to just include the parallelism in our machines. Quantum gates, measurement, you all are known, because everything what we people are putting here, that must be executed through the gates. Yes. And we know once you have explored the quantum system, that quantum system will be full of all possibilities. Yes or no? But from all the possibilities, we have to extract the desired outcomes. Okay, that would be based on our measurement apparatus. So we have to take care that what we people are going to retrieve from the system itself. But anyways, once you start measuring your system, or once you have measured your system, your quantum state of the system would be definitely lost. Yes or no? Yes.
Yes, sir.
And we immediately transform to the what? Classical outcomes. So that is the basic processing. We usually take what? The classical data. If the machine, the classical machine, is not enough capable to process the thing, so the same thing to be processed by the quantum machine, but the quantum machine cannot process 0 1. So for that one, initially we have to encode our information from zeros ones to cat zeros cat ones. Yes or no? That must be the responsibility first. So once that information representation is ready, so now the machine will process the information. Clear? So now after processing the certain that is data, the machine will generate some output based on some programs, and the program must always be there in the form of quantum programs. Okay, so now everything, because once you have measured the outcome, means it should belong to what? It should belong to the classical outcome. So, and you people have learned it in the last classes, you must have learned it, that the quantum algorithms, that is for writing any of the solutions, we usually propose the quantum algorithms. Okay, but why the quantum algorithms are proposed? Because this quantum algorithm gives us the analogy of writing the solution, okay, in a quantum domain, and this algorithm part we usually understand. So this is as per the human specific nature. Okay, we usually give the solution in the form of algorithms. Okay, so but the machine, the quantum machine, does not understand such algorithms. So we have to encode, or we have to transform the same algorithm into what? Quantum circuit format. Okay, so once your quantum algorithm gets transformed into a quantum circuit format, so that quantum circuit would be executed on the quantum machine. Do you agree with this fact or not? What runs over the quantum machine?
Yes, sir.
Do you call it as to be algorithm? No. Okay. What we usually run? We usually run for quantum circuits. Okay. So we have to transform the quantum algorithm into equivalent quantum circuit. But you should know there would be a bidirectional that is arrows. Okay. If you are able to transform your quantum algorithm to quantum circuit, so from the quantum circuit also you can transform it to the algorithm. Means the machine will understand the quantum circuit language. We people being a human will understand what? Algorithmic language. Okay, but we people are the designer of our algorithms as well as the machine, because we are at the early stages of development of the quantum machine. So we have to understand the languages of both the things. Understood? Yes.
Yes, sir.
Okay, so now here what the machine is giving us a guarantee. That is the first thing. high speed of computation, because we know exponential number of operations can be realized in a parallel. Okay, so means for whatever the data processing is there, for such a requirement, the classical machine will be processing for the entire amount of data, but the classical machine can process it in a single step. So similarly, this quantum machine is giving us the possibility of realizing the task that is in an efficient manner for the intensive one as well as for expensive one. Expensive means the data involved in processing a problem is at least an exponentially large, and if intensive we are talking about, means the problem is exponentially at least hard, okay, to solve through the classical machine. Now the other context must be coming to picture, that is the time complexity is reduction, because if we are giving a parallel solution, so anyways the time complexities will be reduced. Okay, and once the time complexities are reduced, so we will be definitely obtaining some speed ups, and this is at least an expectation that the exponential speed ups we people are expecting from the machine. Okay, whether it is based on the hardness of solving the problem or it is based on the data, which is at least an exponentially large to solve that problem. Okay, so another fact is that the quantum machine is having a privilege to represent the high dimensional data. Okay, so these all are basically the guarantee which is given by what the quantum machine. Now comes down to what the why we are looking for machine learning. We know that every machine learning task, if we talk about the generalized category of the task, so it belongs to either what supervised learning or unsupervised learning, or apart from that one we can also take it as one other branch as a reinforcement learning method. Okay, but here you have to just understand the fact whether it is a supervised learning, unsupervised learning. We have to check that what kind of a data set, what kind of features we have. Okay, if suppose the data set is contained with the features, like we have input features, we have the labeled output feature. Okay, so if we have a labeled output feature, so we have to just take that particular task to be considered under a supervised learning task. But if no such labeled output features are available, means we have to understand the underlying structure of the data itself in order to recognize certain patterns. Okay, so for that one we have to go for unsupervised learning tasks. Okay, so if we check for the supervised learning task, so that supervised learning task can be again classified into what classification and regression task. Okay, like for categorization of something and to predict something. Okay, and we know whenever the output labeled output data may be continuous in nature, we people are looking for certain predictions, like house price prediction we usually talk about. Okay, but if our data is just classified, okay, if our data is labeled as certain categorical things, so now like an email based features we people are processing, and we have to declare whether the data or the email is a spam mail or it is not a spam mail. Okay, or for a particular image we have to declare whether it belongs to a cat or it is not belonging to a cat. So these classification regression problem both are considered under a umbrella of what, that is a supervised learning. Now another where we have to just look forward, we have to understand the underlying pattern of the data, that is the structure of the data, in order to come up with some patterns. Okay, like customer segmentation problem. Okay, like we have to just segment the customers, we have to understand their buying behaviors. Okay, we have to understand the overall behavior of the customers, that whether the customer are basically for any purchasing system the customer, or for any shopping system the customer is a frequent customer, or it is just a greedy customer, or it is just an optional customer when he comes or not comes. So there are several things that we have to consider. But why this machine learning to be here integrated with the quantum field? Okay, because there are some viewpoints for which the quantum has to answer. That is the first thing we are looking for. We are always looking for the scalable model. Okay, we need the efficient writing of the algorithms, like machine learning algorithms. Okay, so we want basically our machine learning algorithms to behave as more efficient. Okay, so in a classical machines we have certain limitations. So but if you want to just make it in a parallelized way, okay, or some parallelism to be included here, we have to go for what, machine learning solutions, that is a quantum based solutions. We can make the model as more scalable as we can. Okay. Similarly, the feature extraction part should be more enhanced, because anyways the feature to be extracted in very efficient manner. Okay. If there are some redundant features, so the model will take more time to get trained. Okay. Now the prediction accuracies, these are also one of the things to be enhanced in perspective to what the machine learning domain. The visualization of the data would also be enhanced. Okay. These are still the viewpoints we people are just looking for. Like this is the another fact, that is when we used to call upon the dimensions or in the features related to our data. Okay. Or the data set, when the dimensions or the feature related to the data is exponentially large, that it requires a very large amount of space to process. So how these features be handled efficiently by the quantum machine, that should be first given by the computational model as in the form of guarantee. Okay. So the thing is what, that there are certain viewpoints, there are certain guarantees that is given by a quantum machine that is expected by the machine learning. That is why some other researchers, experts have just integrated both the domains and they come up with what, that is the context of quantum machine learning. Okay. So now this is just about a basic thing that is to be understood and to get motivated by yourself, that how we people are approaching to a quantum based machine learning solutions. But here comes the picture. Okay. Like you people must have known the fact, that is in a classical machine we know a Michael J. Flynn has given some classification, okay, of parallel processing capabilities. Yes or no? Like SISD, SIMD, MIMD, MIMD. Yes? Yes?
Yes,
Okay.
sir.
So now the thing is that based on instruction stream and a data stream, the Flynn has classified the 4 parallel processing machines, whether it belongs to SISD, SIMD, MISD and MIMD. So like SISD, like we usually talk about, I told you earlier also that the quantum machine is giving us an intrinsic parallelism. The machine is, that is the hardware is giving us the privilege to realize the parallelism. But such a parallelism may not be involved here in what? In a classical machines. We people being a human, we apply intentional parallelism in a classical machine. Do you agree or not? Like at the lowest level of processing, if you see here, SISD, like pipeline support we usually give. Yes, some vector or parallel processing is also allowed. Whether if you talk about the processing related to your multi-threaded environment, or if you talk about the multi-core based processing. Okay. But if you have the multi-processor based processing or a multi-node based processing also, that would be coming to the up hierarchies. Okay. So the thing is that starting from the lowest level of parallelization, we are expecting to achieve what? Highest level of parallelization. Okay. Like from the pipelining step, we go ahead with what? That is a multi-threading concept, coming up again, looking for the multi-core based realization, coming up again, multi-processor based realization, multi-node based realization. Okay. So the thing is that if we have the certain capabilities that we can incorporate it in a classical machine to just retrieve some parallel outputs. Okay. These are some things to be intentional. But what are the target areas? The target area is number 1, that is SIMD. Single instruction to be processed by over the multiple data. And this is the ultimate target. That is what? MIMD. That is multiple instructions to be processed over a multiple data support. So here in the same context, some hybrid classifications the researchers have been proposed. Okay. And this classification is now categorized into on the basis of what? The type of data and type of algorithm. Here the CC stands for, that is we are looking for a classical data and the algorithm is also classical. So if a classical data and a classical algorithm is there, means any form of the parallelism we are incorporating or not?
No.
Yes, at least yes. Why? Because if you are looking for the CC, means classical data to be processed by classical machine, so we can achieve such kind of parallelism, whether it belongs to any one of them. Yes or no? Okay, but it would not be like quantum. But the thing is that if we are going for what, the classical data to be processed by what, the quantum machine. So that is actually the first target, to learn the quantum machine learning model. That usually I have given you the example. We are usually taking the data in the form of classical data. Yes, the classical machine receives the data in a classical form. If the machine understands that the machine is not efficient to solve that problem, that the same data to be transformed into the quantum compatible format. Once that quantum compatible format of data is ready, then we have to hand over the same data to the quantum machine. So now the quantum machine will start processing. Okay, so this is the first target. Like this is SIMD, this is that is CQ. Okay, that is the classical data to be processed by the quantum machine. This is another, that is what do we call it as, quantum data to be processed by classical machine. Now you understand in the previous slide. Can you let me know that the information representation of both the computational models are completely different or same?
Different.
Yes. So how come it is possible? Okay, we have to just, again, if you have the quantum data, you will have to transform it to the classical machine. Okay, then only you may process. Otherwise, you have one more thing that is to be called as inspired task, like the quantum inspired task. We have to just simulate what, the quantum behavior for realizing the classical computational tasks. Okay, so that thing we also can consider, but it is still included for what, the completeness. Like here MISD, it is included for what, the completeness of this classification scheme. Okay, like MISD, multiple instructions, we usually do not process it on the same data. So similarly, the quantum data need not to be processed by a classical machine. Okay, but this is the ultimate target, the quantum data to be processed over a quantum machine. So this is our ultimate target we people are looking for. But we do not have any privilege right now, that because the data sets which are openly available or publicly available, they do not belong to what, the quantum data. Okay, so we have very small world. Okay, so we have very small world right now in the context of the quantum machine learning realizations. Okay, but the ultimate target is what, to have the data set in the form of quantum encoding, and the same data to be encoded over a, that is to be processed over a quantum machine. So this is basically the realization what we people are having in our mind. Okay, that is, the classical machines are basically not made for the parallelization. Okay, we people being a human include the level of parallelism in a classical machine. Okay, but the quantum machines are basically providing this inherent parallelization feature, because it is supported by the hardware itself. Okay, because the quantum mechanical principle of superposition may be realized under a computational model, and this is allowing us to realize what, exponential number of operations in a single step of execution. Like for a 1 bit, like for a 1 qubit. Okay, how many quantum states we have that may be realized? How many quantum states?
2.
2. Okay,
Two
for
states.
2 quantum bits, how many quantum states?
4
4.
states.
Similarly, for n number of qubits, the total number of quantum states would be 2 raised to the power n. So that is why I have been letting you know that exponential number of operations, these are some exponential number of operations. Sometimes it may belongs to operation, sometimes it belongs to data. Okay, but these all things may be realized by only having what, n number of quantum bits, because it is supported by the architecture itself. We are not here to just include any level of parallelism. Okay, this is hardware supported parallelism. So now this is the advantage that we people are going to take and to include in a quantum machine learning tasks. Here you see, that is the overview, that is the first thing. Before proceeding to anything, you just see this hierarchy. Okay, here at the top, what we people are having, that is a quantum machine learning domain. You do not think like that, okay, there is no such work or very few work have been done. People have been working on a quantum machine learning almost, if you see, that is onward 2018 and 19, the lot of works the people have been proposed. Okay, So right now, if you just go for your literature survey also, so you will find n number of solutions. Almost all of the classical machine learning tasks have now been transformed into the quantum one. But I'll let you know what are still the scope of working. Okay, there is nothing like that the things are ended here. Okay, because we are still there in the early stages of development. Nothing developed or nothing proposed can be set as a benchmark. Okay, so just rely on this fact and keep working. Okay, such that like you just try to understand in the earlier days, like if I am letting you know about the sorting algorithm. Okay, so for sorting your n number of elements, so earlier we have some very basic solutions in the form of bubble sort. Yes or no? Yes.
Yes, sir.
Okay, but that time when the bubble sort was proposed, no one must have thought like, okay, some quick sort strategy, merge sort strategy, like heap sort strategy would be proposed by the other people. So the similar thing is that if for a certain problem, if a solution is already proposed, so it doesn't mean that the solution is now over. For solving a particular problem, we may have n number of solutions. Okay, and it depends. It depends that which solution would be fruitful based on which data set. Okay, so now the thing is the quantum machine learning may be categorized. This is as per one of the that is referenced work. That is what? Either fully quantum machine learning or it may be hybrid quantum machine learning. So now you talk about which one to be considered as fully quantum machine learning. That is QQ.
QQ.
Okay, and what must be the hybrid one? That is a classical data to be processed on quantum machine. So
CQ.
here we are looking for what? QQ approaches. Here we are looking for what? CQ approaches. Okay, so now the thing is that if you see this diagram, this has here been ended. Okay, because lot of things have not been done based on QQ, because the quantum encoded data to be work on the quantum encoded algorithm. Okay, that is on a quantum algorithm. Everything is not quantum. Okay, but there is lot of work. There are lot of works have been already done in the form of hybrid quantum machine learning solutions. Okay, like if you talk about the optimization problems, like kernel solutions, neural network solutions, and we have very dedicated solution in the form of parameterized quantum circuit. This is as per the basic quantum strategy only. Okay, these are the strategies you must have heard about your machine learning domain, like optimization problems, kernel problems, neural network problems. If you look forward for the approximate optimization algorithms, okay, like for annealers, like for variational eigensolvers, support vector machines, clustering algorithms, encoders, okay, like neural networks, recurrent neural networks, generative adversarial networks, CNN problems, so many that is models. Okay, so many models you must have already learned in a machine learning domain. So but this parameterized quantum circuit is basically perfectly based on what? Quantum domain. Okay, it belongs to quantum. So this is one of the model preparation. It is one of the kind of the model that may be proposed in the form of quantum solution for your task. Like for a classifier, I am still interested to just transform the support vector machine into the quantum based support vector machine model. Okay, so that is the one task. Otherwise, the same classification task you may perform using the parameterized quantum circuit. Sometimes it may be called as variational quantum circuit. Okay, I'll let you know that what would be the variational and parameterized quantum circuits are there. Okay, in the letter that is on the day after tomorrow. Okay, because in the next lecture I'll let you know that what is basically a context of parameterized quantum circuit. So if you see this hierarchy here, okay, the people are still exploring what? The hybrid quantum machine learning models. Okay, but why only this one? Because the machine, the programming machine is giving us the flexibility. You people have learned the concept of Qiskit programming? Yes?
Yes, sir.
Have you explored some of the programs, or have you coded some of the previous algorithms or the basic concepts using a Qiskit?
Not during
No,
this
sir.
FDP. We learned earlier personally.
Personally, okay. So in this FDP, it is not done. but
It
it's
is not.
okay. Okay, it's okay, but I'll try to just connect you with all. Okay, so because I am very much specific to the machine learning model, so I will just, because still we are restricted to the session, no problem. So but you see here, the Qiskit programming framework is giving us the features, okay, like in an open source library, quantum community is there, so many quantum codes you may find, and these are openly accessible on a GitHub accounts. Okay, circuit visualization is also possible. If you see the application modules, there is a dedicated library or the package that you may call it as a Qiskit machine learning package. Okay, so based on that package, you may use the ready-made model, or you may use directly your your ready-made or your ready models that is equivalent to your classical model, whether it belongs to a regressors or it belongs to a classifiers. Okay, so the programming model is basic, or programming framework is giving us the flexibility, okay, to code these machine learning problems. Okay, to code the machine learning problems in a quantum domain. Okay, and we have some community engagements, so many things, everything, educational resources. If you talk about the from beginner to advanced level of target audience, everything is already considered. If you refer the Qiskit.org itself, you will find n number of resources to learn the Qiskit programming framework. Okay, but here the context is other. That is, if you see that what must be the pipeline that is usually work here in a quantum domain, this is as per the classical. How do we process any machine learning solutions? We usually we consider the problem. Okay, based on the problem, we have to just find out some of the data sets, and based on that data set, we try to just use our machine learning algorithms. Okay, so that machine learning algorithm is basically taking your data set in order to just train the model. Okay, so once your model is trained based on certain input data, we have to just go for start prediction. Okay, we have to go for start predicting the outputs. So this is the basic pipeline. But what is here transformed in a quantum domain? You see, we usually have a classical data, because where we are in a CQ or QQ. Yes, CQ. So if you see that by default our data set must always be remaining in what? Classical. So if you are ready with your classical data, okay, so initially, because we know the classical data must be in the form of what? Zeros, ones. But we do not know about, because the machine will not understand zeros, ones. Machine will know cat 0, cat 1. Okay, that is, so for that purpose, we have to just encode our classical data into what? The quantum compatible format. So some quantum encoding techniques we have to understand. Okay, that would transform our classical data into the quantum data. Once your quantum data is ready, we have to feed that quantum data to the learning algorithms. So that learning algorithm will take your quantum data and it starts learning from the data and prepares the model. So once the model gets trained again, okay, so we have to just look forward for the measurement, whether that is our quantum encoded data is now to be transformed again to the classical data. We have to check it for, and after that one we have to look forward what? For the classical data prediction. Still for everything the pipeline is same. Classical data, whether it belongs to a training data or a test data, we have to just first convert the data into the quantum encodable format. Once the quantum encoded format of data is there, that is to be trained by what? The quantum based machine learning algorithm. So if the model is now trained, we have to check for some training predictions. Okay, now follow to that one, we may test some outputs based on some random outputs, so random inputs of data. So the thing is that what is there in a pipeline? So in that pipeline only these two things are additional, that is a quantum encoding and further measurement, because we know once the quantum exploration of or the quantum system is over, everything is classical. Do you agree this thing or not?
Yes, yes, yes.
Once the quantum processing over, everything is classical. Yes. So now remember this fact, that what is important at all? during the entire pipelining, this is the pipelining I am letting you know. So under this pipelining, we have to be more focused first on what are the data encoding mechanism, because we people are here. What is the context? What is the title of our today's lecture? That is foundations. We are still looking for some foundational aspects of dealing with the machine learning, that is quantum machine learning. Yes or no? Yes.
Yes, sir. Yes, yes, yes.
Now here you see, this is one of my proposed ladder. Okay, so this you try to understand, very simple one to understand. Initially we have to come up with what? Some problem definition, and we have to formulate the problem and check whether the classical machine learning solutions are feasible for that problem or not. And for all of the problems what we people are having, we have the machine learning specific problem nowadays. Yes or no? That is solutions nowadays. So once you are ready with your problem defined, your problem is defined or your problem is formulated, and you know that machine learning solution exists verbally, okay, then what is the next step? We have to check for the quantum feature mapping to a quantum stat, because whatever the data features we have, okay, so that feature we have to encode in a quantum format first. For that one, we have certain encoding mechanisms like basis encoding, amplitude encoding, angle encoding, and there is a specific feature of a cascade programming framework. I'll let you know in the later slides. That is called to be a ZG feature map. Okay, so that ZG feature map will help us to take what? To encode our data and to map on the quantum circuit. Okay, now follow to that one, we'll look forward for what? The machine learning algorithmic selection, because we have to check whatever the solutions were feasible initially, we have to categorize whether it belongs to a classification problem, regression problem, or it is for the clustering problem. Okay, based on that one, whatever the machine learning algorithmic selections were there, we have to consider all of these machine learning algorithms here. Okay, and now the task is what? To transform that machine learning algorithm to what? Into its equivalent quantum algorithm. Okay, so if the machine learning algorithms to be encoded into the quantum algorithm, like I have taken a jump. Okay, so quantum algorithmic model means what? We have to look forward for the quantum circuit designs of the model. Okay, so for that one, that is the circuit model, we have to come up with equivalent to the quantum machine learning model. For that purpose, we have to come up with what? The designing strategy that we have to choose. We have to choose that what kind of design strategy we people are applying. Like you people may recall, most of the people I am considering, they belong to a computer science. Yes or no? Yes.
Yes, sir.
Maximum.
Okay, so I am still assuming that the most of the people must be belonging to computer science now. So in a computer science, when we learn the course like a design and analysis of algorithms, so there are certain design strategies for the algorithm or not, like divide and conquer. Yes, like greedy method. Okay,
Yes, sir. Yes, sir.
so like dynamic programming, branch and bound, several design strategies we people are having. So similarly, basically we take such design strategies to write the solution in the form of algorithms. Okay, so here also in a quantum algorithmic design, we have to choose some design strategies, and you people have learned it out, like quantum oracle. Okay, quantum amplitude amplifications. Yes, you people have learned it. I know what the things I know already. I have
Yes, sir.
checked out your previous schedule. Yes, these things like quantum Fourier transforms, phase estimations, quantum walks, hybrid algorithms. Yes. So if you know these all, the design strategy, that which design we have to opt for the particular design of the algorithm. Okay, so a strategy we have to choose first. Okay, based on that one, we'll come up with some circuit designs. If the circuit design is ready, we have to optimize that circuit also. It is our responsibility, because we people are there in early stages of development. We do not have enough powerful quantum machine that can execute any size of the circuit. Yes or no? If you people are certainly known with the IBM quantum machine itself. Okay, so the machine is giving us some certain restrictions to us or not. for the realization of the codes. Yes.
Yes, yes, yes.
Okay. So now just I request you all, just please respond. Okay, because I am also taking that online session. So online session means it somehow just make us bores. Okay, but so we require some interaction. That is why I usually keep my that camera on. Okay, so that I may be attentive to you all, but it's okay, no problem. Just please respond at all. So the thing is that once your circuits are ready, then you will have to choose some execution strategy. Whether your quantum circuit means equivalent to your model, your quantum circuit may be feasible to execute on a simulation aspect, or it is feasible to execute directly on quantum machine. Okay.
Sir,
So
we have got a little idea of about quantum oracle only, while
okay.
other quantum Fourier transformations and quantum amplitude others perhaps are not being discussed by any of the speaker in the FDP.
I think because you people have learned the concepts, as I already just checked the schedule. Okay. I think the conceptually the things must be discussed. Okay. I think or somehow you just check your other part. Okay. So, but it's no worries. These are some design strategies. You just please understand right now. No problem. Okay. Hello, sir.
Fine, sir,
Okay.
fine.
No problem. Okay. Wherever the context starts. Okay. So we have to just keep it in our mind. That is the context. Okay. So
Correct.
you just please take these things in your mind, that based on certain design strategies, we are looking for some executions. Okay. Once the execution strategy is ready, whether we are simulating our model or whether we are running our model onto the dedicated quantum machine, based on that one, we have to check. Somebody has unmuted the mic. Just please keep it on mute. Whoever is whose mic is
Unmuted, sir. Sorry for the disturbance.
no problem, sir. Thank you.
Correct, sir. Correct. Got it.
Got it for what, sir? Pardon, please. I
Got it for
actually lost.
only this the query which I actually raised that we had not gone through in detail,
Oh, it's
but
okay.
you have made a very perfect similarity between the algorithm which we actually studied in analysis of algorithm part, like dynamic programming, greedy methods,
Yes,
branch
yes,
and bound, etc.
yes.
So the idea is that we do have algorithms like QO, QA, and all these are designed.
Yes. The same thing. And I will discuss in detail also in the later slides. No worries. Okay.
Got it.
No worries. I'll connect. So that is why I told you, whenever the context started, you just please keep it in mind. Okay. I'll connect it further. No problem. So now after this, classical post-processing aspects are also required, because once the quantum model execution is done, the results must be there in the form of classical outcomes. Okay. So we have to evaluate the results as we used to evaluate. Okay. Based on certain metrics or some defined criteria, what we people are already having. Like we usually look for our model performance. Okay. So we have to define our metrics criteria for the comparisons, like the accuracy values, precision values, recall value, F1 score. So these all things we have to consider. Okay. So based on the machine learning, conventional machine learning performance criteria, also you may also go to evaluate your model. But this is not only your responsibility ended here. Okay. You have to look forward for the correctness and the completeness proof for your quantum model. Okay. Because you have proposed the new model for the processing. Okay. So if you have proposed the new model, so you will have to validate your solution mathematically, and you have to set up or declare it as a benchmark model right now in the current in context, because everything is available in an early stages of development. I think the context must be clear to you. Yes, this is the ladder we have to follow when we usually work with what quantum machine learning models. Yes.
Yes, sir.
Okay. Now, so come on to the picture. That is the basic fact that we people are going to talk about. That is the quantum state preparation and the data encoding mechanism. So if you remember that hierarchy, that is this pipeline. Yes. If you remember this pipeline, so again, I am going to discuss the same. Classical data to be encoded, further go for machine learning processing, that is quantum processing, measurement, and go for classical prediction. So here you see the same. Classical data we usually feed as an input to the quantum machine learning. Oh, sorry, as a quantum machine. Okay. So initial task is what? The classical data to be encoded into what? The quantum compatible format. So if the machine is ready, okay, so machine will only be ready if the data is perfectly encoded in its own processing format. Okay. Now the thing should not remain in zeros ones. The thing should be there in what? Cat's values. Yes or no?
Yes, sir.
So now after encoding mechanism, we go for what? The process. That is, process belongs to your algorithm, whatever you are going to train. After that one, we have to measure. Okay, once you measure your outputs, so everything would be just in the form of classical outputs. So this is the basic pipeline we have to just follow. So what is the significant part to discuss? This is the encoding. Okay, so for encoding purpose of our classical data points, like every data set must be containing some data points. Okay, so these classical data points to be encoded, there are actually till now we have 15 different data encoding methods. Okay, but all of them so need not to be discussed. So I will try to discuss some basic encoding mechanisms like basis encoding, amplitude encoding, and angle encoding. And based on these three only, you will be able to realize your quantum state. Okay, so the context is what is the encoding here? Like in a classical data, everything is available in 0-1 format. Okay, but the quantum data, what do we call it as? What? Cat 0, cat 1. Where it belongs to? It always belongs to what? Hilbert space. Yes or no? It's a
Yes, sir.
complex, it's a complex vector space that allows the inner products. Yes or no? And
Yes.
also allows us to measure the information either in terms of length or in terms of angles. Yes, because
Yes.
every qubit is to be treated as a vector. Yes or no? That moves
Yes.
around throughout the sphere. So if you keep this visualization in your mind that your qubit is going throughout the sphere, okay, so every time there would be a phase related information associated to your vector, as well as there would be somehow significant information related to the amplitude of the vector. Okay, so both of these things are allowed from the Hilbert space already to just get our information. So now how the quantum states, how the classical data points are basically to be transformed into the quantum states, such that these quantum states would be explored over the Hilbert space. Okay, so now this is the point we people are just going to discuss. That's the quantum data encoding. What does it mean? It's a process converting your classical data into the quantum state. That is the basic context here. Okay, the classical data, we have to take it as an input and we have to encode the same data into the quantum output, that is quantum states. Here you see that is the first form of the encoding, like a basis encoding. So in a basis encoding, whatever the classical data points we have, like x1, x2, xn, n number of data points we have. So all of these data points actually be encoded here in the form of basis encoding method. Okay, like in the form of cat operations. Okay, like this is what your cat operator of x. Okay, and this x must be comprising of what? X1, x2, and x, and so on. So like if suppose you have a classical data of x, this is one of the example I have taken. Okay, so if you have that classical data of x and this x,
big complex
hello, any queries? Any queries?
No, sir.
Sir,
Somebody
I have a
has
query.
unmuted.
Yes.
Somebody
Sir, I have a
unmuted.
Yes, madam, please proceed.
Sir, in the last slide, we have seen that in the classical methods, we have used a simple machine learning model. But in the quantum flow chart, we have used a quantum machine learning model. Is there any difference between simple machine learning model or a quantum machine? There are different ones
Yes,
or same ones?
they are different, completely different. I told you in the earlier slides itself. Okay.
Okay, but that means they are okay. They are.
Just please listen to words. Okay. If you have the
Okay.
classical model like support vector machines you have, okay, but whatever the perceptions you are having in respective to the support vector machine, okay, the same support vector machine model would not be there in a quantum model. We have to
Yes.
transform that support vector machine algorithmic things into the
Into
quantum
quantum.
circuit model. Okay.
Okay.
That quantum
Okay.
circuit model would be somehow completely different from your classical processing aspects.
Okay. That should also be converted from the classical model to the quantum model.
Quantum model. Okay, that is the first context I told you. If you remember
Is there
this my slide.
Yes, sir. Is there any predefined models that is similar
Yes.
like in machine?
Yes, I will demonstrate in the next lecture. Okay.
Okay, sir.
There are
Okay.
ready-made models. I told you that the Qiskit machine learning. Here I told you Qiskit machine learning.
Yes, sir.
is a specific package that allows
Yes.
us to take the already built model. Okay.
Okay, sir.
Pass the data. That data will
Okay.
be taken by the that is model. It will again be trained. Okay. After that, one
Yes.
to pass our test results, and we have to check for the accuracy of the results. Okay.
Okay.
All things
Right.
possible. And we have the dedicated model in the form of quantum models, like the parameterized quantum circuits. Okay. These are
Okay, sir.
three different models. Like a classifier, I am going to just develop. So that classifier would be completely different. Okay. That is the form
Yes.
of writing would be completely different. Already I
Right.
told at that slide 1 itself.
Yes, sir.
Why these things are different? You try to understand the concept. Okay.
Right.
Because
Right,
the
sir. Right. Got it, sir.
information processing here in classical and information processing there at quantum, both are completely different. Okay.
Yes, sir.
If the
Yes,
things
sir.
are different, so their methods would also be different.
Different. Right, sir.
So we usually call it as analogous things. Okay.
Right.
So analogous things we people are developing. Otherwise, the quantum will have their own models. Okay.
Yes.
So like here you understand, suppose we have a classical data X and this data is available in binary format. Okay. Like this 1 0. It's a binary format of data. Okay. Now this binary information of 1 0 cannot be processed by the quantum machine. Do you agree or not?
Yes.
Okay. So what we are supposed to do? We have to transform this classical data into the quantum state. Yes. So how the quantum state would be prepared? For this 1 0, we have to come up with this basis state. Yes. This is what? 1 0. So this
So,
state
sir,
of 1 0.
So, sir, it is something like this, that we have a 2-qubit quantum system.
Yes,
And
sure.
Okay.
And how
Okay.
do we write this 1 0? How do you write? This is 2-qubit system. Okay. It's a 2-qubit system. Is it a
It is a 2-qubit
Yes.
qubit.
Yes, sir. Yes.
If it is a 2-qubit system, you just please remember my words. Okay. We always expand our qubits onto the Hilbert space. So that state should also be, this quantum state of 1 0 should always be there in a Hilbert space. Yes.
Yes, sir.
So for 1 qubit, how many dimensional Hilbert space is explored? For 1
Two.
qubit, there is 2-dimensional Hilbert space. Yes.
Yes.
Like
Yes.
cat 0, we usually write it as what? 1 0. And cat 1, what? How do we write it as? 0 1.
0 1.
Okay. So how would you be able to write this 1 0?
0 0 1 0.
It's a 4-dimensional space. It's a 0 0 1
0
0.
1 0.
Yes. So this is your actually data. Okay. So at the vector form of the processing, at the lowest level of processing, this is the vector that will be containing your data. But in the quantum state format, we have to encode like this. If you have a classical data point like this, we have to transform it to an equivalent quantum state. Understood? Yes.
Yes, sir.
Now here, another method is to have the amplitude encoding. Means now you know the amplitude, the concept and the significance of the amplitude. Okay. So if you have any classical data points, that classical data points can be encoded in the amplitude of that is the data can be embedded, or the data can be that is encoded in the form of amplitude itself. Means the vector will be just containing a load of representing the data. So now here, if you see, if we have suppose a classical vector like this one as the vector we have, and we have to transform it, or we have to represent that vector onto the Hilbert space as it. So now This is a superposition state we usually consider, okay, like a probabilistic function. Okay, so now the probabilistic function we people are defining here in the form of cat psi. So here what we people are looking for, that is 1 by norm of the vector. So if x is a vector, okay, so this is to be called as what? The norm of the vector. And how the norm of the vector be calculated? That is under root of squares of their point values. Yes or no? Yes. So suppose one of the norm of the value, 1 divided by norm of the vector. After that one, we have to take the summation, because it's a probabilistic distribution of all the data. Okay, so the summation of I equal to 1 to n, okay, because there would be n number of data, that is the data values contained in a vector. Now, associated to each of your quantum state, we have certain values. Okay, so now when we see, if suppose we have x1 and x2 as the two different data values, okay, like x1 is 3, x2 is 4. So based on that one, we usually calculate what? The norm of the vector. So norm of the vector be calculated as 3 square plus 4 square under root value. So once you calculate it, this value would be equal to what? 5. So now your data value like x1 and x2, it is available in classical. So classically your data value is looking like 3 and 4. Yes. But in a quantum world, your data is not like 3 and 4. Rather your data be written like what? X1 prime with the value of 3 by 5, x2 prime with the value of what? 4 by 5. Okay. So because the data to be represented with what? With the factor of 1 by mod, that is the norm of the vector. Okay. And the norm of the vector is calculated as 5. Okay. So it is now your classical data of 3 and 4 is now available in a quantum compatible format of 3 by 5 and 4 by 5. Okay. So what is the importance of this amplitude encoding? That for your number of data, okay, we only need to take log of n qubits. Okay, if suppose you have the n number of quantum states, okay, so for n number of quantum states, we have to take what? The log of n values. Okay, so for, you do not write it like equal. So for n number of quantum states representation, we have to take the log of n values. Okay, like if you have 8 number of data, okay, there are 8 data. So now to represent the 8 different states of a data, how many number of qubits we require? 3.
3.
Because with the 3 qubits, we can be able to encode our information. So the same thing is that, because it's an amplitude encoding factor, and the data is now encoded in the form of amplitude itself. Okay. Now followed to that one, we have angle encoding method, where the data that we are taking as an input, like n inputs are available. So n inputs to be encoded using n number of qubits. Okay. So every time the classical data is to be encoded here in the form of some rotational angles. And these rotational angles will again form some quantum states. So the classical values, like any of the xi classical value we have, okay, so that classical xi value to be encoded here in the form of rotational angle. Okay. So like any of the rotation to be performed based on some theta value. So that theta value over this ith value of I, that is x, be calculated as a function of x of I. Okay. And that function of x of I be defined here as in the form of superposition. That is still a probabilistic distribution we are looking for. And this is some rotational angles. So rotational gates, so I think you people have already learned, like Rx gate, Ry gate, or Rz gate. Yes?
No.
I think you must have completed these all. Okay. In your
Sorry, in fact, we have already covered some Hilbert space, unitary, and very simple things, perhaps.
It's okay, but
and that too in the very first lecture.
But
correct me. Other participants may correct me if I am wrong.
okay, no problem. Again, I would suggest that it is still beyond of my context right now, because we have very limited time as per our scheduled lectures. Okay, no problem. But you remember and do believe on me that these are some gates. Okay, these gates perform some rotations onto the block sphere. That is onto the qubit on which the gate is applied. Clear? Like Hadamard we apply on any of the qubit. What happens? what happens if we apply
Yeah,
the
Hadamard also make some phase shift.
huh?
Hadamard when connected with some.
Hadamard performs the creation of superposition.
Yeah,
Yes.
yeah.
1 by
Yes.
root 2 times. 1 by root 2 times.
That is not always to be called as or you may call it as like if you have a quantum state cat 0 and applying Hadamard on that one, what do you get? You will get the cat 0 plus cat 1 by root 2. Yes,
Root
or
2.
and the same state you write it as what? Cat plus. Yes,
Yes, sir. Cat plus.
Yes, yes,
that
yes.
is the same thing. Similarly, I am letting you know that if you have a gate like Hadamard, similarly you will have some rotation gates like Rx, Ry, Rz. So these perform actually certain rotations about X basis, Y basis, and Z basis. And you, if you know the block sphere theories, okay. So based on the block sphere theory itself, you may get to know that how the rotation about Z axis, how the rotation about X axis and Y axis would be performed. Okay. But based on that one, we will be encoding our data. And if you do not know, so just do not be worried upon anything. I'll demonstrate everything through the Qiskit program. Okay. So you will have certain visualization over the data representation. Okay. The quantum machine learning task would be completely different. Okay. What we usually work upon, what that is with the classical machine learning solutions. Okay. Still the that is the basics, fundamentals are same. Okay, but the things are different. Now here if you see in an angle encoding method, we are free to use any rotation gate. I told how many rotation gates? Rx, Ry, Rz. Yes. If you
Yes, yes, sir.
if you remember, let me draw this. This is suppose block sphere. Yes. At this block sphere, at the north pole, what do we have?
Cat 0.
Cat 0, here cat 1. Yes.
Yes.
So this is what your Z basis. Okay. And we have another basis that is called to be X basis. So this is what your X basis. Okay. And here you take, it's a 3-dimensional structure. So here you take, it's a Y basis. Okay. And it is the center of your sphere. So on these, we have some equator ring. Okay. I'm not going to just take because this is the equator part. Okay. So once you apply the Hadamard, on this cat 0, what is the resultant we get?
Cat 1 complement.
No, sir. No, sir. Here I told, if we apply the Hadamard on cat 0, means it is just like if you have a quantum bit Q0 that is already initialized to 0 and we are passing a Hadamard gate here. Yes.
Yeah, root 1 by root 2 times.
It is what? It is transforming your cat 0 state to plus state. That is cat 0 plus cat 1 by root 2. Okay. So here, if you see the block sphere, so here, this is the position where your vector comes. Okay. And when your vector comes here, means it starts moving throughout this equator ring and it keeps continuing. Okay. So here, this is on the X basis, this is plus basis. Okay. And if you go or expand it to the negative side, so here you at this point you will receive what? It's a minus basis. Okay, that is a minus state on the same X basis. Here you see another state would be there. That is, what do we call it as I? And in this negative direction, you will have what? The minus of I state. So there are 6 different basis states that we can have over the block sphere itself. Okay. So similarly, you try to understand either on Z basis or on X basis or on Y basis, we can perform certain rotational operations. Okay. So it will perform some rotation based on what? Some theta value. Okay. Means we have to pass some angles. So based on certain angles, some rotational transformations will be performed. Okay. It's all about the space theory. Okay. If you have a vector as in the form of information, yes, so you would be having some matrices, yes or no? Yes. You have the information as in the form of vector. So do you need any matrices or not to transform your vector from one position to another position?
Yes. And that is actually how.
That is only the
actually
purpose of matrices.
Sir,
Yes.
that is actually how eigenvalue comes into picture here also.
Yes, that is the context. We actually explore the total energies which are contained within the quantum state of the system. Okay. But from that one, we have to extract the desired energies. Now, extracting of the desired energy from the complex quantum system is similarly like extracting the eigenvalues from the matrix.
Sir, right, sir.
Understood? So now you start connecting with these facts. So now this encoding is particularly useful in what? Variational quantum algorithms. I told what is variational quantum algorithms? These are a specific part of the algorithm, like this parameterized algorithm. Yes, like a parameterized quantum circuit or variational quantum algorithms. They both are the terms that can be interchangeably used. Okay, so just do not be confused with these things. So this variational quantum algorithms actually needs the encoded classical data in the form of quantum states. So here if you see, if we have the quantum states, the classical data, which is initially encoded as cat zeros. Okay. Now here which encoding we are applying? Angle encoding. It is still an angle encoding, but based on what? Rx. That is based on x direction or x basis. Okay. But here if you see, the same initialized data is to be performed with certain rotation, and the rotations are performed using what? Ry. Okay. Here if you see, this is your initialized data, and now we have to perform the Rv operations. But these Rv operations can only be performed if before that one the Hadamard's are applied. So this is only the difference to apply with the Rv. You just remember this fact. Z gate, that is a phase gate, you learned or not? Like polymetrices. Yes, polymetrices or polygates, you learned or not?
No, sir, yet to learn, sir.
This is X, Y, and Z. X gate, Y gate, and Z gate.
Yeah, poly X gate we have learned, sir.
Already learned, na? Okay. So the thing is that X gate, Y gate, and Z gate, there are the three specific gates. Okay. So based on that one, we have some Z gate. So Z gate is having certain metrics like this 1, 0, 0, -1. I am not using all because still I am running out of time. Okay. And we have to just complete. So now try to understand. This is Z gate. So if you perform the Z operation on the zero initialized state, like if you perform the Z operation on 0, there is no change in 0. 0 will remain 0. This I am letting you know. You just believe on my words. Okay. Now the another thing is, this is Z. When you apply on the one initialized quantum state, okay, then this one becomes -1.
-1.
Okay, this one becomes what? A -1. So because we know that the Z have no impact on zero initialized quantum state. Okay. So similarly, because if you have a quantum that is the initialized position of your data as cat zeros, so and if you directly apply RZ, so there will be no impact. Okay. So what will be change that is to be done here? That is to apply the Hadamard first, because once you apply the Hadamard, your 0 will become what?
Plus.
Plus 1/√2, and within that equiprobable superposition there is a possibility of 1, and once that possibility of 1 occurs, this RG operations be applied there. Understood? Okay.
Yes, sir.
Yes,
So
sir.
now you compare. These are the three encoding methods we learned: basis encoding, amplitude, and angle. Here you see, in a basis encoding, if you have n is the length of your supposed data, so the same n length of the basis vector you have to create or not?
Yes, sir.
Okay. Here in angle encoding, again, if you have n inputs, so the n qubits of that is n number of qubits to be used or not? Okay. Like this, each of the qubit is to be passed through the rotational gate. Okay. So still, if you see the qubits, the required for basis and angle encoding, both are order of n. But here, if you see the amplitude encoding mechanism, what is the number of qubits required? Log of n. Okay, so the log n qubits are required here. But if you check for the complexities, basis encoding is really simple one. Okay, we can directly take the binary string. That binary string can be encoded into what? Quantum encoded format. Yes or no? Okay,
Yes, sir.
that 01 you are taking, you are making it to cat 01. So it's simplest one to just go for. But amplitude encoding is really hard one to realize. You remember, it's still this encoding method or the data encoding is one of the open research problem to our computer science domain right now. Okay, and angle encoding is basically taken as moderate, or you might consider it as a medium level, because the same angle encoding mechanism will be used by the Qiskit framework, and that is to be called as ZG feature map. Okay, and the same length of the n number of qubits would be required there. So their interpretability, that how we will be interpreting the quantum information, so highest interpretability will be there in the form of basis encoding. Similarly, in an angle encoding also, because we know that how much is the rotational transformation we have applied onto the data point. Okay, but here in an amplitude encoding, the interpretability of our encoded values may not be really very a simple one to understand. I'll demonstrate through the Qiskit program. Then you will get to know the complexity of understanding the data representation here in the quantum domain. Okay, the things are really different. So like the basis encoding you must have used in the logic gates, like XOR gates or any of the other gates you people have learned. Okay, for large vectors, we have to check for what? The amplitude encoding, because if you have very large number of data vectors, so for that one amplitude encoding would be really sufficient. But you remember, this is hard to realize. We do not have still a very enough powerful computational model like in a quantum representation model that can represent all the large vectors of information in the amplitude of the data itself. Okay, and for the other that is task like quantum neural networks, you may use the angle encoding method, or for certain problems like whether it belongs to a support vectors or it belongs to a solutions related to the amplitude estimations. For everything you will have to work for what? Angle encoding method. So remember that angle encoding method is basically taken care by what, or it is expanded with over what? The ZG feature map, and it is one of the feature that is provided by what? Your what do we call it as? Qiskit framework. Understood? Now this is the talk required for the basis, that is a feature mapping using a kernel, but it's already 9 now. So what I would recommend you, okay, to or I am just asking you first whether do you agree to go for the visualization of or these data representation through the Qiskit program first, or let me continue, or you want me to continue with the theoretical aspects? Because if we cover this one, so the practical aspect would be covered in the next class. Okay,
So we would like to go with the Qiskit, sir.
Qiskit right now. Any other people, what do you suggest? Because it's
Continue with the theoretical part, sir. Later, tomorrow we can have the practical section.
okay.
Sir?
Krishna Shastri sir, why you raised hand? I saw raised hand. And for what? Theoretical part.
Most probably unfortunately he pressed it, sir. We will continue with theory, sir. As we have a hands-on session day after tomorrow.
So there only we will just map again. Okay.
Yes, sir.
No
Yes,
problem.
sir.
So here you just because already we are late, it's 9, but I will extend my class by 20-25 minutes. Okay. So just please, it would take time. So just please, because the things are really complex to understand. You just please try your effort. Okay.
It is our pleasure, sir. If you extend, we are ready. No issue.
Okay. Thank you very much, sir. So now look forward. Oh, my pen is not working. Just wait. Just wait for a sec. It's now working. No, now, so look for the feature map. Okay. Now you understand what is the requirement of the feature map here. There are two contexts to be discussed. That is the first thing. We have the classical data. Yes. The classical data to be encoded into the quantum compatible format. Yes or no? Yes.
Yes, sir.
Yes.
So under a quantum compatible format of a data, we have learned three different mechanism, either the basis encoding mechanism, amplitude encoding mechanism, or suppose angle encoding mechanism we may apply. Do you agree or no? This thing? Yes.
Yes.
Yes,
But
sir.
if you have a data like this, but the same data to be there onto the quantum circuit itself. Understood? So what is the context of feature mapping here? You just try to understand that we people are actually, the feature map is here the quantum data to be just loaded onto the quantum circuit. Okay. So that would just create our feature map first. So that is the one context. Other context may also be there. Other context may also be there. Then once we try to transform our data, okay, from a lower dimensional space to the higher dimensional space. Such a model we used to work it like a suppose vector machine, because once we apply the classification task, okay, so under a lower dimensional space our data may not be classified. Okay, so because the data may not be linearly separable, so once we find or the model finds, then the data may not be linearly separable. So for that one we require some transformation of our data to the higher dimensional spaces. Okay, so for that required transformation, the people will be applying the feature mapping concept here. So here, these, with the basis of these two encoding mechanisms like these, whatever the data we have available in n dimensions, we are performing some functional task that would just transform our encoded data into what? A form of m dimensional space. And if you remember the context, whatever the machine learning task we usually deal with, okay, these tasks are basically limited by a polynomial space. Do you agree or not? Yes.
Yes, sir. Yes, sir.
Space problem. Okay. So everything means our data should be there in a polynomial space. If it goes to an exponential space, so there exists certain inefficiencies of the classical machine learning models. Yes. So the thing is that we know that we people are learning here one other aspect of computation like quantum machine. And the quantum machine is having a privilege to explore our entire data onto what? Exponential space. Yes or no?
So, sir, sir, I have one curiosity here.
Yes.
In fact, we usually in a machine learning algorithm like support vector machine, and if we already have the data in high dimensions, then we use some dimensionality reduction techniques to make data more simpler by reducing the dimensions.
That is the prerequisite. That is the requisite task. That is
Right,
to
sir.
perform
Right, sir.
before support vector.
Right, sir. But
Yes.
what actually we are doing here, we are of course first we are actually trying to convert data from low dimension to high dimension. Fine.
Yes.
Okay, it may be due to the fact that quantum machines can be able to handle, right? First stage.
Not only quantum, the classical ones also doing in the same manner.
Second thing is, in fact, if actually we are making our data more complex, then why we are not relying only onto the classical models which were fairly doing the task?
So who says that the quantum model is not doing the task in a fair manner?
Now, see, sir, we are actually trying to convert the data from from Rn to Rm.
Okay. It's a dimensional space, n dimension to m dimensions.
Yeah, n dimension to n dimension, and of course m are relatively higher than n.
Yes.
So are we going in the right direction? It means we are somehow challenging the dimensionality reduction techniques like PCA, SVD, LDA, and all that dimensionality reduction do we have?
Yes, that we may apply because we used to reduce the dimensions. Okay, because still right now, to what the transformation, this is all about the transformations. Okay, So the first transformations we people are just performing because the data is not linearly separable. We cannot just apply any best fit line there. Okay, that can classify your data points. Okay, so for that purpose, you people are just transforming it to the higher space, such that in a higher dimensional space you may be able to classify your data points. But
Yeah,
the
something like
visualization
kernel
of the
tree.
same data
Something like kernel tree.
that is the kernel transformation. Okay, that is the topic we already had. This is the title of this section. Okay, so such a kernel transformations are always be available. I told you there are two different contexts that we people are going to learn here in a feature mapping. Okay, so in the context of the quantum feature map here, we do the similar thing, like we have to encode the classical data into the quantum Hilbert space, because the Hilbert space is remaining as what? The exponential space. It's not like a polynomial space. Yes or no?
Yeah, right.
Okay, so whatever the inefficiencies were there in a classical model, the same inefficiencies would not remain in a classical model, quantum model. Okay, but we do not have the enough powerful machine that can expand entire data set over to the Hilbert space. Okay, we are limited with the processing of the qubits. Okay,
Right, sir, right.
okay, so now so basically the context of the feature map is taken here to encode our what? The classical data into the higher dimensional Hilbert space. Okay, so that we will be usually called as what? The quantum feature map. So now the context is that if you are dealing with the high dimensional Hilbert space, so over a high dimensional Hilbert space, we should have some privilege through the quantum algorithm itself, through which we will apply some similarity measures or to check for some distance between the data points. Okay, so these aspects actually would be used. Okay, it would be used just to apply any machine learning task, whether it belongs to supervised, somehow it belongs to unsupervised. Okay, so but we have to take care that how our data points be represented over the exponential space. Okay, like on to the Hilbert space, and how the similarity measures will be taken care, and how the distances be calculated there. Okay, so the concept of the feature map is here coming into the picture, that the quantum computer that is already known to explore our data into the exponentially large Hilbert space, that is the first thing. Okay, so everything is available onto the Hilbert space format. Now the feature map, the feature, if you remember the first slide, what I started discussing, that is the concept of a viewpoint, that what the viewpoint is having with the machine learning aspect. Okay, so the feature map encoded with that is to encode our classical data into the quantum state, that we have to take the classical data, encode it into the quantum states, and that quantum states to be that is loaded onto the quantum circuit. Like if you have you learned the that is the concept of Grover's algorithm? Yes, Grover's done.
Yes, yes.
Yes, sir.
If you
It's done.
remember the Grover's algorithm, the concept is very simple. Whatever the data we have to mark, okay, the data that is to be marked by a oracle, we have to pass this data to the oracle or not?
Yes, sir.
And before passing that data, we have to expand the entire search space. Do you agree or not?
Yes, sir. Yes.
So once after exploring the entire search space through the Hadamard transformations, if you remember the circuit of the Grovers, initially all Hadamards followed by oracle. Oracle will take the input of the marked element. Yes, based on the mark element, it marks the quantum state. Once the quantum state get marked, okay, it would be further amplified through the diffusion operation. Yes or no? And if you remember the circuit of the diffusion operation, there would be several Hadamards in a parallel, followed by X gates in a parallel, followed by the last qubit must be initialized with some Hadamard, followed by multi-control NOT gates, followed by the reverse transformation of the entire circuit. So what does it mean? The mean is very simple here. The data along with the algorithmic part of the circuit, both should be there onto the quantum circuit itself. Okay, so that is why I told you in the start, at the start itself, that everything should be there in the circuit form. Data should be there on a circuit. Your algorithm should be there on a circuit. Okay. So your algorithm will automatically process your quantum encoded data and start measuring their output. Okay. Once you just stop your quantum system. Understood? Yes.
Yes, sir. Yes, sir.
Okay. So now the thing is coming into the picture like a quantum kernel. That is an analogous to the classical thing. That we if suppose we people are just operating on a high dimensional space. Okay. So the quantum kernel will be just taking care of some similarity function. Okay. That is to check for the two quantum states through the feature map. Okay. So because that now the concept of the feature map would be different. Now the feature map would be there onto the quantum circuit itself. Okay. So if something or the things are there onto the quantum, that is what do we call it as quantum circuit itself, then how do we go for measuring the state? Okay. Whether they are likely state or they are similar state or not. So if you see this is the kernel function we people are taking, and that kernel function is now encoded, because if you see this is what modulus square operation. Okay. This modulus square operation, and these are what the operation I have taken. This operation, what do we call? It's an inner product. Yes or no?
Inner product. Inner
Okay.
product.
So the inner product we have taken, and we know what is the values of the inner product. If we take the inner product of 0, 0, what does the value?
0.
1, sir.
Yes. They
Sorry,
are
sorry, sorry. Sorry.
They are likely. Yes. If in place of 0, if both are 1, then still the answer is 1. But
1.
if you have like 0, 1, okay, the answer must be what? 0. Because
They
at
are
that,
orthogonal to each other.
yes, they are orthogonal to each other, and not only to be called as orthogonal, because every qubit gets expanded over the Hilbert space. Okay. And that Hilbert space representation of your qubit must be there onto the block sphere. Okay. And block sphere, we know it's a unit sphere. Yes. So at a unit sphere, if the quantum states are suppose orthogonal to each other, that to be called as orthonormal. Okay. Okay. So if
Right,
we
sir,
know,
right.
so if we know that how do we measure the similarity between the two quantum states, then we have to perform the inner product in a squared form, because once you perform the modulus square on that one, means we are looking for the probability associated to measure the answer. Yes, that is the concept of measurement. Yes. So now if we have suppose a state as 1, means if we are getting the output as 1, means the states are identical, or based on similarity they have been chosen. And if you are getting the output as suppose 0, then at that time your states must be called as orthogonal to each other. So this is how we have to check it over, that is whether the two quantum states are identical or they are similar or not. And we have to check it onto the kernel space. Now, overall, the context what we people are looking for, that is the feature map. So the feature map is looking for the quantum circuit that is basically used to encode our input data. So whatever the input data we have, means the data is already encoded. Yes. Now the encoded data we people have just loaded onto the quantum circuit. So if the data is loaded onto the quantum circuit, that would be now considered as our feature map. Okay. So there may be several possibilities to design the feature map. Earlier, like a basis encoding method, amplitude encoding method, or the angle encoding method, these methods we used. Okay. And based on these methods, we have transformed our data onto the quantum circuit. I'll demonstrate it to you through the Qiskit program in the next class. Okay. That how I can demonstrate right now also, but it's already running very late of time. So no worries. I'll let you know. So now come down to the concept of a ZZ feature map. So ZZ feature map, I told you that ZZ feature map is basically what? It's a parameterized quantum circuit, and it would be just using that the quantum circuit would be there, and that quantum circuit be prepared using some encoding methods. Okay. And we know that what encoding method I told you that time itself. What encoding method? Angle encoding method to be used again in a ZZ feature map. Yes. Yes. So based
Yes,
on
yes.
that one, if you have any parameterized circuit, that must be available in the form of entangled values and followed by some Z rotations. Okay, so Z rotations would be applied. So how this ZZ feature map be actually prepared, I'll let you know here. That is the ZZ feature map that is implemented by a Qiskit, or it is supported by a Qiskit framework, where your n inputs like x1, x2, and xn on n qubits would be just like used as an angle embedding method or angle encoding method. Okay, and based on these angle encoding methods, we will be just preparing some, that is quantum circuits. Now here, this is the way through which we can form the quantum circuit. Like what, how to do? Here, if you see the circuit, these are the input initialized. Okay, that is the initialized quantum states. After that one, what? This, if you know, we have done it already in the angle encoding or not? If you see this one, yes.
Yes, sir.
Yes, sir. Yes,
Okay.
sir.
So now this is just like same. So if you see at the step number 1 that how the ZG feature map be created based on suppose 3 inputs we have like x1, x2, x3. So apply Hadamard on each gate. So we have applied Hadamard on each gate, followed by what? Apply on each qubit J a rotation, that is a rotational transformation using RZ gate. Okay, and it should be based on the twice of xi value. Okay, so whatever the data point values are there, we have to just multiply it with the twice factor and just encode it. Okay, so this is your encoding. Now after that one, we have to find out the pair of elements like jk. We have to take, like this is suppose 0, 1 and 2. So we have to take care of the elements of q0, q1, q0, q2, and q1 and q2. And based on these three, if you see A, B, and C step, what we are doing initially at A, we are applying a C0 gate. C0 gate, that is what? If it is from JK, so J must be taken as what? The control qubit, and K must be taken as a target qubit. And at the step number C, if you see again, this is what? Again the C not gate is applied, but in between another Z is applied. So this is the first Z, this is another Z, and this Z, rotational Z transformation is applied based on what? Twice of, that is pi minus of xj value and pi minus of xk value. So whatever the data points are there like x1, x2. Okay, like if x1, x2 are involved, so that is pi minus x1, pi minus x2, these values to be deducted, and it would be a twice multiple of that one, and we have to perform the Z rotation. Means coefficient that is within the bracket of this RZ, we are passing the angular information. Hello? Any queries?
No, sir, somebody has mistakenly.
Okay. So now if you see, this is one part of the circuit. That is the ZZ is prepared among what? That is between these two. Now if you see, this is between what? The first and third. It has been created like in a similar manner. It is like another one. So if you see, this is the way your quantum data is actually be represented. On the quantum, that is on the quantum state space, and that quantum state space be called as what? Hilbert space. So the thing is what? This ZZ feature map is one of the programming supported feature that is popularly known to just make our feature map using a Qiskit programming. Okay, so I'll let you know in the next class with that one. Now some other essential things are there, like this is one of the aspect to be learned about the quantum memory. Okay, because without a quantum RAM, nothing is possible. I told you at the start that the quantum machine is known for realizing exponential number of operations in just a single step of execution. Do you agree or not? Okay, so suppose these exponential number of information is already contained in my quantum RAM. So I should have some privilege. Okay, I should have some mechanism such that the quantum processor, the quantum processing unit would be enough capable of retrieving entire quantum words which are contained in our what? quantum memory. It means what? If you have n number of qubits, so with the n number of qubits, 2 raised to the power n, this is the size of your RAM or not? What is the size of your RAM? That is 2 raised to the power n cross of m. Yes or no? Yes? Yes or no?
Yes, sir.
Yes, yes, sir.
Okay. So if
Yes, sir.
if you have 2 raised to the power n number of addresses, so to realize these all addresses, only we require what? N number of qubits. With the n number of qubits, all 2 raised to the power n number of address locations be expanded in just a snap of execution. So if suppose you are dealing with an exponentially large amount of data, so that data you should take inside what? The quantum RAM. And under that quantum RAM, if you have certain mechanism through the quantum processor unit, that through which every location or each location of or every location we used to take a term like every location of a RAM can be accessed at a time, then we have the enough powerful computational machine. Means there would be a compatibility matching. Yes or no? My machine can perform exponential number of operation. Now the RAM is enough capable to get the access of what? Exponential number of data in just a single step of execution. So everything would be completely parallel. Okay. So this is just about the one of the other tool which is requisite for what? Machine learning foundation. Another thing is related to some swap test, because we have to check anyways under the Hilbert space expansion. We have to check whether the two quantum states are overlapped state or not. We have to check whether the states are similar to each other or not, or whether they are different states or not. So for checking as a similarity measure among a quantum state, we have certain test, and that test to be called as a swap test. And for this swap test realization, we have very simple circuit. There should be a designated qubit, okay, that is to be taken as control, okay, initialized to 0. And these are the two different qubits. Here we assume that this is a quantum state A, this is the quantum state B. And what gate we have used here? What is the name of this gate? What is the name of the gate?
Adamant gate.
No, it's a swap gate.
Oh,
Okay.
that's
So if you take the consideration of swap gate, okay, so this swap gate actually swaps the quantum state. Okay, like if you have a state like A and B, so when you perform it through the swap gate, your quantum state would become like BA. Understood? A and B would be interchanged. Understood? So now, but this is not only
Yes.
it is a controlled swap gate, like a control NOT. You must have learned it like a control NOT gate. Yes. So like this a C NOT, it's a C NOT. Similarly to that one, we have the controlled, it's a controlled swap gate. Okay. So based on that controlled swap gate and based on these two Hadamard applications, we can at least be able to measure whether the quantum states are similar or they are orthogonal to each other. And we already just discussed this fact earlier, that what is basically the context of realizing that how do we check whether the two quantum states are similar? We perform the inner product, yes, and the inner product results must be 1 or 0. 1 or 0.
Sir, if
What?
it results 1, then they are similar. If it results 0, then they are orthogonal.
Then they are orthogonal. It's okay. So initially this swap test always retain with some probability, that is probability to obtain the 0 quantum state. Means in order to obtain this answer with 0.5, means we will understand if the probability of this measuring this quantum state of 0 here, because this is the measurement operator is applied. Okay. So if it is still 0.5, then we will understand that the A and B, which are the quantum states, they must be orthogonal. But when the probability becomes 1, means the probability of measuring the 0, if becomes 1, means we will understand that the quantum states would be identical. So it is one of the tool. The swap test is basically a tool here in order to check whether the quantum states over the large expanded Hilbert space would be identical or similar, or they are not similar. Okay, for that one we have certain mathematics. Okay, for that one we have certain mathematics in order to check whether they are similar or they are not similar. Okay, like an initialization we have taken like A and B. So initial state would be what? That cat 0 would be there and AB is there. After applying the Hadamard gate, we know that this 0 becomes what? This 0 becomes 0 plus 1 by root 2. Yes or no?
Yes, sir.
So
Yes.
AB remains AB. After that one, we apply the swap gate. So once we apply the swap gate, I told you what happens. AB becomes BA. So now here the states be transformed, because now at this state, this is 0. So there is no impact. But at this state, this is 1. So because this is 1, so AB will be swapped to BA. Okay, now we have the superposition of this state. After that one, again the Hadamard to be applied. So once you apply the Hadamard on this 0, this would become what? 0 plus 1 by root 2 again. So if this becomes 0 plus 1 root 2, so now this one is 0 of AB and this is 1 of AB. Okay, so 0 plus 1 by root 2. And what will happen to this one? If you apply the Hadamard on 1, it would become what? Cat 0 minus cat 1 by root 2. So this is regarding BA. So we have what? BA. So now on BA, it is still associated to cat 0, and this minus of BA is associated to what? Cat 1. So like this wise, because 1 by root 2 was the earlier probability amplitude, and right now the 1 by root 2 is again multiplied here. So 1 by root 2 multiplied by 1 by root 2, it becomes 1 by 2. Okay, so there is now the half chance. So now the half chance comes. Okay, so if this half gets added here in the probability of 0, then we will declare that the quantum states are identical, otherwise the state would not remain identical. Clear? Okay, so now this is as per the measurement process. So once you apply the measurement process, okay, if you see these things, like once you apply the measurement on 0, that is probability of measuring the answer as 0 onto this 0. So on this 0, so it would become 0, 0. And if you are looking for the probability of 0 on this 1, so there is no possibility. That is 0 on 1. Yes, because we know this entire term will be cancelling out. Yes, but this one will become 1. So once you expand this expression, we'll have again the certain possibility to measure the answer as what? Half. Okay, so if this half factor gets associated to what? Your previous half, because already that half value is considered with what? Probability of 0. So that half plus half will become what? 1. At that time, we will be declaring at the Hilbert space itself that the quantum states are identical in nature. Otherwise, there is no identical quantum states. Okay, now come down to another fact. That is the last one. I already connected it with the earlier factor, that how do we go for quantum machine learning design methods. Okay, so the classical algorithm design methods, like we know, divide, conquer, greedy method, dynamic programming, backtrack method. Okay, we have some basic quantum design strategy. Like quantum parallelism, you people have learned it. So this is one of the design strategy. Okay, and based on this design strategy, you people have already covered Deuce and Deuce-Jozsa algorithm. Have you covered it already or not?
Yes, we are already covered.
Based on the quantum amplitude amplification, this is the design strategy. Okay, like quantum parallelism. So one of the design strategies is amplitude amplification, and it realizes the task of quantum interference. And based on that one, the Grover's algorithm, you people have learned it. Okay. Similarly, the quantum Fourier transform, inverse quantum Fourier transform, they both design strategies have been taken to form the quantum phase estimation technique. Okay. And based on the quantum phase estimation technique, only the HHL algorithm, it is one of the famous algorithm actually, what we call it as Horo, Hasidim and Lloyd algorithm. So this algorithm actually solves the linear equations. What it solves? The linear equations. Okay, so system of linear equations be perfectly solved by the HHL algorithm. Okay, and phase estimation is one of the inherent technique to design the HHL algorithm again. And these all things are requisite. You just believe on this fact. Okay, these all are requisite to transform your classical machine learning model into the quantum machine learning model. Okay. Now here, some of the open research problems which are still available in a quantum machine learning. When we see for the scalability, because this was one of the viewpoint of what? The machine learning, that it should be scalable model. So whether we will be able to scalable up to a large extent for building up our quantum machine learning model or not. Okay, and how do we able to reduce the noise? Okay, because the error corrections, these techniques are always be there, because the quantum machines what we people are dealing in the present era, what do we call these machines as? NISQ machines, yes or no? What is the mean of NISQ machines? Noisy intermediate scale quantum machines, yes or no? Okay, means we have the quantum machines that may realize the noise. Okay, so for a real quantum machine we have the noise, so we have to take care. And this is still open research question remains in a machine learning, that whether the all models will be scalable or not up to a large extent, noise reduction would be perfectly possible or not, how the efficient design of the quantum algorithm be there. Like I told you, the people have designed the classical equivalent quantum model, but how the model be optimized, how the quantum circuit be optimized, that is still how the quantum data encoding. I already told you 15 different quantum data encoding methods we already have. Okay, but you are still available, or you are still allowed to propose your own encoding method. Hybrid, how the classical or the hybrid quantum classical model will work in actual. Okay, up to a large extent. Optimization and training techniques, how the machine learning problem be used as an optimization problem, how the techniques be actually incorporated here in a quantum domain. Benchmarking, performance evaluation, it is still there, that is an area of open questions. Okay, so these things are always be there in your mind, because I told you we are in the early stages of development, not related to the quantum machine, it's relevant to entire machine learning domain. Okay, so these are certain applications I told, that is a machine learning algorithms. They are looking for like support vectors. So these support vectors for classification purpose cannot be directly designed. Here in quantum, one madam asked the question. So now you may focus. Okay, now madam, you please focus, or the other people also may focus here. Like the variational quantum classifier would be a dedicated circuit for realizing the classification task. Kernel mechanism can also be implemented here. HHL algorithm is one of the tasks, that is to solve the system of linear equations. Okay, like for least square algorithms, for a regression task, we have to solve the system of linear equations through HHL algorithm. So again, the design strategies are coming into the picture. Okay, without the design strategies, so we cannot do any of the that is machine learning task. Like for k-means algorithm, for the clustering task, we need the quantum distance estimation method through the swap test. So once the swap test get done, then only the minimum distances we calculated. Like the neural network parts, like for deep learning applications, so optimizations and related to the high dimensional data representation, we need some quantum feature mapping through the parameterized quantum circuit. And I told you at the start that the not only we are looking for the artificial intelligence, it's the time to come to move down for the artificial intelligence to the quantum machine intelligence aspects. Okay, so but looking at these QMI aspects, the classification pattern recognition task can be enhanced. Okay, similarly the NLP task can also be enhanced. Okay, that we will be discussing in an application area of the next lecture. Okay, because already half hour is over. Okay, so large scale data analytics may also be supported by an approximation and optimization algorithm. So the quantum is having a dedicated algorithm. And you should know that AI task, certain optimization problems, they will be really get benefited through what? Through the Grover search algorithms. This is one of the tasks that you may be performed through the using of the other developed algorithms or the design strategies in parallel. Now, this is all about the concluding remarks of our session, that throughout this session, I tried to convey the information related to the quantum machine learning, that under a machine learning task, we are supposed to first understand how the data be encoded. Okay, because if you don't know the data encoding and their representation, then we can't understand what would be the possibilities of the quantum model. Okay, and the quantum data would definitely map our classical data into the quantum states. And we know basis encoding, amplitude encoding, angle encoding, there would be several different mechanisms. But ZZ feature map would be supported by the Qiskit feature. And it is really helpful for the machine learning task, because the ZZ feature map be used in a parameterized quantum circuit. Okay, or you may call it as variational quantum circuit. I'll discuss this one in the next lecture. Okay, this is actually one of the form of just developing our model using a quantum task. Okay, and the swap test, we know that it is used to compare the state of the quantum, that is to check for the similarities of the quantum states over the high dimensional spaces, that is explored over the Hilbert space. Okay, and the quantum memory is really necessary for what? For accessing our quantum stored data. So this is all about our today's lecture. We have now completed this one. These are certain references. I'll suggest this one because you must be known with the reference of this is the standard, like Bhagavad Gita. It's a book. Okay, like Michael Nelson and Isaac Chuang. If you read this book, you really find it well. Okay, you just go through, you will get to know everything about the quantum. But there are certain books related to the quantum machine learning, like Peter Wittig. It's a good book, but it's only that is devoted to the data mining techniques. But if you see for the Xavier's book, like a machine learning theory and application, so you will have certain quantum mechanical aspects. Some quantum machining aspects the people will include. Okay. Similarly, the Zhang Ficard, this book I'll recommend you to just go for. It's very simple book to understand, to read down, and it's already it is available freely. Okay, but there are certain papers. These are not only the papers, if you see, like quantum algorithm for beginners, quantum machine learning for data scientists. Okay, like a systematic categorization of a quantum machine learning. These papers must be of length 80-90 pages. Okay, so it would be somehow like a handbook. Okay, like a small book. And you may also just learn your quantum machine learning context through the IBM experience. Okay, not only that one, we have certain designated library. I'll let you know in the next lecture itself. Okay, so this is all about today's session. If you have any queries, so still I'm available for you all people. Any yes.
Sir, first of all, thank you very much for your patience and enthusiastic session,
Okay.
sir.
Thank you, sir.
Even though it is 9:40, you are with the same tempo, the tempo which you have started.
Thank you very much, sir.
And fortunately, I still have 168 participants actively in the session and asking questions. Really, sir, thank you very much. We are
Okay.
rigorously waiting for your next session, sir.
Yes, sir. In next lecture, so we will have very limited time, because consecutive to my lecture, there is another lecture schedule. So
Yes, sir.
we have no scope of expanding our class anyways, but we will have the practical realization along with the hands-on experience to our
Yes, sir.
quantum or Qiskit coding. And so we will demonstrate with some practical models of the quantum machine learning. Okay. And
Yes.
see you all. And it would be really my pleasure to again be connected with you all people. Okay.
Thank you very much, sir.
Any other queries if you have, so you please let me know. Thank you. Thank you to
Thank you very much, sir.
Thank you to you.
Yeah, we learned a lot today, but we need to work on for the next within 2 days. We will work on it, sir. By day
Yes,
after tomorrow, we will be ready.
Yes, sir. Sure. Please.
Thank you, sir.
Okay, sir. Any other person?
Thank you, sir. We will make a call. Thank you very much for your
Okay.
nice session, sir.
Thank you very much, sir.
Good night, sir. Good night.
Okay, good night. So should we call this end of the today's meeting?
Yes, sir.
Okay.
Thank you.
So Murthy sir, just I'm leaving this meeting. Thank you very
Yes, sir.
much.
Welcome, sir.
See you day after tomorrow, sir. Bye.
Welcome, sir. Thank you.
Good night to all participants. Okay. All the best.
Thank you, sir. Thank you, sir.
Thank you, participants, for your patience, learning and staying in the meet. Good night.